Okay, so thanks everyone for joining. I'm not sure if Professor Christian Enz is going to join today, but we have his PhD student. So, and the update today is going to be about the Skywater 130 measurements done on a test site from Skywater. And Hanchi has been working on that for the past few months, I guess, or a couple weeks. So go ahead, Hanchi, and
Yep.
you know if Christian is going to join or not? Can
I
you?
just I just sent him the message, and I'm still waiting for his message reply. So I'm not sure.
Yeah, he said he's going to join, but let's see.
Yeah.
All right. So
All
are
right.
you ready?
Yep. All right. Let
Cool.
me share
Go
my
ahead.
screen. So good morning and good afternoon, everyone. Today we would like to present our some preliminary silicon results from the Skywater 130. So this is today's agenda. I will show you the measurement setup and some result, and finally there are some useful links for checking out. In EPFL and Neuchâtel, we in the micro city we don't really have the fully automated probe station. Instead of that, we have the probe station like the figure like this one, and we control the switch matrix and also the semiconductor device analyzer, and together with the probe card, and this way we can run some kind of the semi-automatic measurement. The only thing that we need to the only bad thing that we need to unprobe and probe it again, but once the probe is touch the samples, then we can sweep from one to one. Eventually, it depending on the devices, but we can run some batch of the measurement at the same time. And to run the measurements, we use some homemade software in Python. This is also can be shareable if you want. And this is just some picture regarding our setup. So this is the probe card. And for the probe card, it has 2 rows of the tips. For each row, it has 12 pins. So, for example, in this figure showing, we probed 2 rows of devices. So, if one row has 7 devices, so we can measure in total 14 devices, probably in 1 hour. And let me share you some silicon results. So in this slide, I would like to show you some preliminary results from our setup and on Skywater in order to show you the capability at the EPFL Neuchâtel. And so I will not go through all the data right now. I'll just show you some selected devices. So here it is an unfit and the structure is mismatched. And I guess it's the smallest devices that I can find from the test structure. And as a left figure showing here, we have the transfer characteristic IDVG for the for the saturation and for the linear VDS. And on the right side is a IDVD output characteristic, and sweeping with different get voltage. Since we also have the open source tool to extract the SEKV parameters, so let's we directly to take the transfer characteristic for VDS, which is 1.8 volts, which is this orange one, and we put into the automatic extraction tool. This is the result. So the markers here, this one, the circle markers are the IDVG in the log scale, and the triangle ones are in the linear scale. And the dashed lines here are the extracted model data, so it fits very well to the measurement and gives some SEKV parameters showing that this is the, for example, the lambda z is 0.17, which is the parameter for the velocity saturation, and which correspond to the 150 nanometer channel length. So it is makes sense that in this with this channel length we have some short channel effects, and of course the threshold voltage and the slow factor and the specific currents. And in this slide shows the PFIC, P-type PMOS, and also it is a mismatched structure and the smallest device. And by showing your IDVG and IDVD sweeping different VD for the transfer characteristic and sweeping different gap voltage for the output characteristic. And it is also, we also use the SEKV extractor to do some extraction on the measurement, and it also works very well for PFET. And finally, we also measure the device that I'm not sure what is this, but this is the unshort, the flavor is unshort.
I think that's the LVT device, or
LVT.
I
Okay.
think this maybe the standard. I forgot.
Okay. And the M is the duplication, or?
Yep.
Okay.
Yep.
Okay, thanks. So we also do this exact same measurement on this flavor, and the IDVG looks great, and especially IDVD has, it's not it looks a bit different from what we saw from the previous slide, but we also try to use the extraction tool to extract parameters, and surprisingly that it fits very well for this data set for the short devices. And there's one thing that we are not super sure is that with this channel length, the lambda z go to 0.5, and usually this is the value for extremely downscale devices like a 16, even 16 nanometer FinFET or something shorter. And
so just curious, Hanshi, have
yeah.
you tried to run simulation using open source tools to compare to your model versus the raw data you have?
No, not yet. This is our next step.
Okay.
Yeah. To do some measurement validation, and eventually we would like to do using the EKV 2.6 or eventually EKV 3 to build up the compact model.
Okay.
So this is a list of the complete measurement. So we measure these two, the top twos are the mismatch structure, and the bottom one is unshort. So for each device, it has an IDVG and IDVD with different VD or with different VG. The last page here, I would like to show you some some links to the repo. And this link is it's not completely correct right now because now we are under the process of the pull request. So this link will be changed later on, but probably I can share the updated one once the my repo is merged to the main branch. All right, so this is just short updates from our side. Thank you.
Okay, great. Thanks, Hangchi. Are there any questions? So basically, this effort is to, is basically the first step to automate the testing and model generation using the test style and hopefully the new open source test style in Skywater 130 and other open source nodes. And Hanchi and Professor Christian Enz has started that effort. I think Akin as well did that initially, but he's more focused on the cryo temperatures. So any questions for Hanchi?
There's a schedule for doing more of the test structures, and how many of the test structures are you going to end up covering?
So we did the first test style. I think you're aware of it, Tim.
Yep.
So that was an MPW5. There's a new test structures from Christian and Sadayuki that we'll probably implement in the next shuttles when that opens up. We did the first one, which is pretty exhaustive based on the feedback I'm getting. But if you have any other structures you think, we can add them.
Well, this particular set of tests is from the Skywater test structures.
Yes, that's the proprietary test structure.
Right, but there are like 100 different structures on that thing. So how many of them?
Yeah, go ahead, Hanchi. Do you have an answer for that?
Yeah. Sorry, I didn't get it. So you mean the structure? This is structure I measured right now.
You tested. Yeah, you tested 3 of the structures pretty thoroughly. So how many of them? But there are like 200 or so structures on this test set. So how many of them do you plan to get to?
Tons of it. Yeah, because now the problem on our setup is that it is a semi automatic setup. We have to move one by one. Yeah. So if we do everything manually, that would take a lot of time to complete all the measurement. I mean, all the structure. And from my side, I would like to select some devices that could be useful, because there are something that I'm not sure what is this on the on documentation. So for example, now this measurement, I only select the things that looks familiar to me, like the N phase, P phase, or some high VT or low VT. I didn't measure the low VT or high VT one, but it could be included for the next measurements. And about the time frame that I need to discuss with my professor, because if we want to do everything, we probably need to get some master student to work on the measurements.
So my understanding is this is temporary because we want to make everything automated on the open source test styles. So this one is the proprietary one, and the documentation is lacking. So it's hard to identify each structure. I think Akin has spent a lot of time doing that as well, right, Akin?
Yeah, there are about 1,100 devices on that. So we measured about like 1,000 of them in the past, like a few months ago or something like that. I mean, it takes time to go through all of them. I agree with you on that one. Just to have a comment about the M. M is the multiplication factor. So that means there are that many devices in parallel. If you see N, it's a fingered device. Like there's also that many in parallel, but that in a fingered configuration. If it's M, it's like it's the same thing repeated that many times.
I see.
So when I get the model, you should divide your measured curve by like 1170. Then fit one device, then just multiply the curve by 1170.
Okay. Thank you for the information.
You're welcome.
Thanks, Akin. So I'm curious, Akin, have you seen any VRAM on that test structure?
I don't have it on the list that I have.
I see. I think that would be valuable if you can spot it, or maybe Hanchi, you can look up for it, like a VRAM device there.
Yep, I can do that. But actually, I have a question. So because now our setup is, you can completely see that it's just a very simple probe station, and if you want to automate everything, it couldn't done on this setup. So my question is that, is it possible to, for example, we have some digital switch parts on the silicon on the test structure. So in this way, we can just easily change the address of the DUT, and we can sweep a lot of devices for one batch of the measurement with the probe is there.
I just want to say something about that one. I think that something like that is okay for room temp, but that I believe you don't want to do that. It's like that is okay at room time, but you don't want to do that low time, because what you measure might be the some kind of leakage current over the mux as opposed to the device itself. So I mean, I think that requires a lot of experimentation to figure out that your multiplexers are not affecting any of the measured curves and stuff.
Yeah.
But
So
at room temp, I think it is perfectly fine.
yeah.
Okay, I see.
So
Because
Hongqi,
now,
my understanding, talking to, so I had a meeting with Christian at ISSCC, and my understanding is looking into the whole automation of testing these chips, right? Or the open source style at least. So did he mention that at all, or would have been good if he was here?
Yeah, it would be good if he is here, because we haven't, you know, we don't really have that much time to discuss since he went back to Switzerland.
Okay.
Yeah.
That's all right. Well, we can have an offline follow up on that, but I think we can implement things on chip. We need to make sure it doesn't corrupt the measurement at different conditions, like Akin was mentioning here.
Yeah. Actually, this is also the concern, because now for my PhD, and we are trying to also measure the same thing with the digital parts and down to cryo. We haven't verified that point, but this is also part of the plan for my PhD. But it's on different technologies. It's from GF1.
Okay.
Yeah, but it seems that because there are some literature, they did this already. They use this kind of structure to measure mismatch. On 40 nanometer bulk. And the result looks reasonable, I guess.
I see.
Yeah.
So Marcus, do you have any comments on the automation part of testing?
I mean, the automation of the measurement itself is something we cannot do either. The models that you're extracting are the EKV models, right?
Yes, exactly.
So they are not suitable for circuit design. This is just a very simple model for plotting one transfer characteristics, basically.
That's true.
So, of course, we can, and I offered that we implement a full extraction in DMT, where we need way more than just fitting one equation. But so far, there has been no, we didn't talk too much about it.
Because another step that we also want to do that is implement the compound model by using EKV 2.6 or EKV 3. And this thing is still ongoing, and Professor Ans is trying to gather the Matthias and Wladek involved and do this.
Yeah, he's trying to open source that version of EKV.
Yeah.
Forgot the number.
Yeah, EKV 3.
But I mean, I'm not an expert on EKV, but I'm pretty sure that EKV 2.6 should be capable of this technology, right?
Yeah, because I think they have tried. Yeah, that's what we can do as well. No problem.
I mean, in
because
the worst case, just changing the model. If we don't change the model core too heavily, the extraction won't change too much. We can just rerun the scripts.
Yeah, that's true.
Well, I think Marcus, to your point here, first of all, getting the raw data is the first step to do any modeling, right? So I think what Hongqi is doing is just giving some fitting and curves of
yes, it's great work. Thank you so much.
I want to quickly comment on your setup. I actually like this kind of setup as opposed to having props like automated, like the moving props.
Yeah.
I think switch matrix and what you're showing here is the way to go, as opposed to having like mechanized props that you just like it keeps moving around.
Yeah.
Because at low temp we don't have that, but we can do the prop card.
Actually, since we are doing that we are going to that way, and we we are trying to mount kind of probe card on the on the cryogenic chamber, and it is not like the probe card, but it is similar to multi-contact widgets. And we already have this from the Pico probe, but now the problem is all the setup together with the probe arm, because the probe itself have 25 pins, for example, and which is completely fine at room temperature. But at cryo, we need to modify, because the size of the cryo chamber is not that big, and we need to change the probe arm. Plus, we need to add more feed through on the chamber, and so it needs a lot of work on the mechanical part. And we already ordered a lot of parts to enable to run the kind of automatic measurement at the cryogenic temperatures. And actually, last month we received the arms, and Lakeshore, the provider, they did a mistake on that, so I shipped it back to the Lakeshore to rework on the program.
So you have like a 1x12 like nozzles or something like that?
Yeah, something like that, and it is compact on a single probe. I can show you some picture if you want.
Yeah, if you just use like a 12x12 or something, and don't ever use the probe arm, you can just use a switch matrix for like 144 of them.
Yeah,
that may be easier, because in that case you don't need to move anything.
Mm-hmm. Yeah. Now then, another problem is that if it's are you talking about the cryo one or the room temperature one?
Both of them. With the cryo, like if you have a much bigger like 2D probe like array,
yeah,
and then you can also connect it to a switch matrix, and just like then at each, I mean, once you're done, you have to like heat up the probe station and like move it again.
Yeah.
But you don't need to move anything in that case.
Yeah,
Basically,
but
that's a lot of measurement.
But another limitation on this setup is the number of the outputs on the switch matrix. I think it's 40, or I think it's around 40 or something. Yeah.
Oh, okay. So you're limited by that, basically.
Yeah.
I think they have switch matrices with like much larger inputs.
Oh yeah. We'd love to have one.
So that may be easier than like moving the probes and stuff. I don't know how we can like land all 12 of them, like keep moving it. So basically you're gonna land them on 12 of them, then you're gonna lift it up and move on to the next one, right?
Yeah.
So it needs to be perfectly like parallel to the chip.
That's true. That's true.
Okay, sounds good. So so Anchi, can you talk with Christian about the automation part, and like what would it take to do that, right? Because I think this is key for us to be able to generate as much data as possible.
Sure, I can talk to him to see whether we have the fully automatic one and the fully automatic setup around APFL. Probably we can reach out to the group and see whether we can do.
Yeah.
This
so he mentioned he's going to talk to Vladek and some other person.
Yeah.
Yeah. The other thing is, do you have any plans to test any other structures or devices?
Not yet, because we don't know which device we should go for, but probably we should, the thing we should do is the validation with the model, right? Or if you have any suggestion on the next devices, you can let me know.
Well, there's a bunch of them, right? There's
too much. So
no, but I mean, I'm talking about the transistors, right? So there's a couple IO devices and a couple transistors. So I think it's going through those. So maybe a dozen of them. Maybe team can help with that.
Yeah, they have some extended drain devices. They have some lightly doped drain devices, LDMOS.
Yeah.
Some of the high voltage ones. Some really interesting things on there.
But do you know the voltage, like the nominal voltage for each kind of flavor?
If I see the device name, I can tell you what the voltages are. Yes.
Okay.
They have devices going up to 20 volts.
Yeah. Is this written down in the documentation?
Some of it, yes.
Yeah. Okay.
So there's some doc that gives the mapping between the S8 or the previous PDK versus the SkyWater 131. So if you're not sure, Hangchi, just email me the devices you're not sure about, and I can help you.
Okay. Perfect. Thank you.
Yeah, that's right. Because if you have names like in short, that belongs to the S8 technology, and that got changed. So yeah, you won't be able to do a one-to-one match of that versus our own documentation that's open sourced unless you have the conversion of names.
Okay. Thanks.
Cool. Any other questions around this topic here? All right, I guess not. So I do have a question. So we're doing some effort here in GF180, but also in SkyWater 130 using open source tools and checking back versus proprietary tools. And basically designing an op-amp, we found that just at the prepex netlist that the results are it's kind of hard to be able to get a design with a precise spec, for instance, noise or bandwidth, or depending on the op-amp we're designing. And Eric, since you're here, so we were trying to compare the results from ngSpice and XICE. So we opened an issue with Sai, who's a collaborator in OpenFA SOC, and one of the things that really isn't understood from my side is how does the result compare at corner like -20 or -40 degrees C. So for instance, we have ngSpice conversion, and we get really, we at least get something out of the simulation, but then when we run it with XICE, it's kind of gets stuck. So I'm trying to understand what the issue is, and or if you guys looked at that issue from your side. Eric, are you there? Maybe not.
So sorry, I am here. I was on mute.
Oh, no worries.
Apologies.
Did you get my question?
So I think I saw the issue.
Yeah,
I think so. So basically, you guys submitted an issue where something was running on ngSpice, but it was failing to run in XICE. Is that correct?
Correct.
And yeah, so yeah, I guess unfortunately I haven't had a chance to dig into that yet, but I can prioritize that a bit.
Yeah, I think that would be helpful. So just some background, we put together some CI infrastructure which runs our generator in ngSpice and XICE in parallel and compares the results. And we also have silicon results from our MPW1 chip. So that helps us basically see how far we are as we go from, I mean, there's no model update, but we make updates to our generator, and we want to make sure it's improving. And it's also a good way to compare the tools. And so, you might get a lot of these questions in the future. So helping us on that part would be really get it.
Yeah, no, I think that's important. And yeah, I've actually been getting a lot of people have been submitting issues and questions to me from outside of Sandia recently, and I think this one just it was one of many, and it sort of got lost in the shuffle. So I'll take a look at it.
Awesome.
All
right.
Yeah, but yeah, I mean, in general, I mean, I think my usual experience is that if there's a discrepancy between XICE and some other code, we can usually figure out why that is. And sometimes it's because there's a mistake in XICE. Sometimes it's because there's a syntax difference. And so but it's usually something that's, a findable issue. So
yeah.
So
okay.
we should be able to find it. I just need to spend a little time on it.
Great. All right, thanks so much. I think
Sure.
a couple follow-up questions regarding XICE. I think it's a great tool, and everyone understands how useful it is. But one thing I'm trying to clarify: do we have transient noise simulation in XICE? Because I think you mentioned there is some support, but I wasn't sure how.
Oh well, if I did, I misspoke. So at the moment, the only noise analysis in XICE is the same sort of noise analysis you can find in SPICE-3, which was just essentially a post-processing step on AC, AC small signal analysis.
Mm-hmm.
And I think we have the expertise to add other kinds of noise, and transient noise would be probably the easiest of the currently unsupported types of noise for us to add.
Sure.
We have a number of people on our team that, at least are from a research group that academically did a lot of research into things like phase noise and stuff like that. So we have people here who know how to do it. The main issue is that, at least within Sandia, there hasn't been a lot of pull for noise analysis, so that just hasn't been prioritized very much. But I keep on hearing this question from external people. It's been coming up a lot.
Sure. But does it mean that XICE is not made for this type of simulations? Because these are very, I wouldn't say basic, but elementary simulation for analog design. So I'm wondering if the use of XICE is more of on the system level to get an estimate of.
Well, I mean, I'm not sure how much I should get into that without without saying stuff I'm not supposed to say. I mean, basically, we have a bunch of fairly specialized applications for XICE internally, and so that's kind of driven a lot of our internal work. But just in practice, I mean, we kind of have to be as similar to the commercial and other open source tools as we can be. So it's actually been on our roadmap to implement other types of noise analysis. It just hasn't gotten the priority level, just hasn't been super high. But ever since we got involved with sort of the open source world, I keep on hearing this from external folks that they really want more noise options. So it is something we're going to do. It's just we're a bit limited in terms of manpower at the moment. I just had a very productive person retire, so
okay.
So it is something we want to do. It's just
I think it's very valuable
to find the time.
Yeah, I think it's very valuable. I mean, especially on the designing at cryo, right? And noise, noise is very important, and it would enable a lot of people, especially in Project Witness right now, and other projects, obviously.
Yeah, no, that's good to hear. So I guess I mean, so there's a lot of different variants of noise analysis out there. I mean, the simplest form for transient noise is essentially kind of like a Monte Carlo simulation, and that I think is relatively straightforward to implement. Sure. It's not super efficient, but it's fairly straightforward and pretty easy to understand. There's other more fancy forms of transient noise. There's a series of papers from Alfred Demir in the 90s where he solved transient noise by solving a system of stochastic differential equations. And that's something I would actually like to implement in XICE at some point, but that's a little bit less straightforward. Potentially we'd have to, well, that would result in a different type of linear system to solve, and potentially that would pose challenges to the solvers and stuff like that. So that's something that's a little more, requires a little more thinking to do.
Sure.
And then also, I mean, people often ask about noise analysis as a, just like you can have noise analysis as a post-process to AC analysis, you can also have it as a post-process to harmonic balance.
Yes.
And we have done a lot of work on harmonic balance recently to make it more robust and productionized. Like the multi-tone capability in the last year or so has gotten a lot better in XICE. But I think, like, if we want to do something like, for example, phase noise, we have to compute something called a phase perturbation vector. And I think to do that, you need to have harmonic balance working well for autonomous oscillators. And at the moment, for autonomous oscillators, our HB capability has some limitations, so that needs to be made better, I think, before we can really do the PPV extraction. At least that's what one of my colleagues who's an expert in this has told me. So anyway, I mean, we have some thoughts about it. I guess probably the first thing we would do would be the most, the simplest form of transient noise, and then go from there.
Yeah, I think that's that could be really helpful. Maybe having a roadmap of all this development would make sense. I know it's
yeah, we've attempted to have roadmaps internally, and then what often happens is that 2 years later we realize we're not following them. So and we have to go back and change it. But yeah, internally we've tried to have roadmaps to varying degrees of success. I guess that's something we could consider making more public. So anyway,
thanks so much.
Sure, no problem.
All right, any questions on this topic? Guess not. So the other question I had is for Team Edwards, and so we've been trying to extract BICS netlist using Magic in GF180 specifically lately, and we noticed some nodes were just hanging and stuff like that. So I think it would make sense if you can give a talk and update on what is the current development, and maybe what could be improved, or how things can be improved, maybe.
Sure. Yeah, I'd be glad to do that.
Thanks.
Yeah, I mean, you want me to do an update now, or?
Well, I mean, you don't have to do that.
Sometime down the road.
Yeah,
I can talk about what I'm doing.
I know your talk from the last year, but I'm just wondering if there was any roadmap or any new developments in your tool. There's a lot of discussion about open sourcing EM solvers and stuff like that. So I don't know how that plugins within Magic and the current tools.
Oh yeah, because I'm constantly doing work on that stuff. So yeah, and it's worth an entire talk, certainly.
Definitely. Okay.
I would also like to know what difficulties you're having, and if you can.
I mean, it's
pass me along some of those problems, I can go take a look at them.
Yes, we'll definitely do that. It's just I think at this point we're realizing that some things are just not right. So maybe it's our misunderstanding, but we'll get back to you, to my students.
Well, given the state that particularly the GF PDK is in, it wouldn't surprise me that there are things that are just not right.
Yeah, I mean, there's
every new PDK. Yeah, every new PDK has little strange things in it that you don't encounter in other PDKs, and so you find the PDK is broken or the tool is broken or something just because it doesn't handle some special case that showed up in the PDK.
Okay, well, I mean, let's schedule that offline. But thanks so much for doing that. And I think the next meeting we'll have is going to be in 2 weeks, or around 2 weeks, and we'll have a discussion around Verilog A compilation and Open VAF from that was released by Marcus, semi-mod company, startup company, and Boris wanted to invite Alessandro and Ken Kundert to discuss this. So hopefully you guys can join and we can discuss it with these guys.
Sounds good.
Awesome. All right, if there are no questions or comments, we'll call this meeting off. And thanks so much, everyone, for joining.
Thank you.
Thank you. Thank you.
Sure.
Thank you.
Thank you.
Looks like I got stuck.